Hello, viewers! Welcome back to Dr. Carminati's YouTube channel, your hub for exploring the most mind-blowing concepts in science and technology. If you're joining us for the first time, I'm so excited to have you here. Today, we're diving into the quantum realm to answer a fascinating question. What is a qubit? Before we get started, I'd love to hear from you. Drop your ideas for future videos in the comments. Share your thoughts. Give this video a big thumbs up and subscribe with the bell icon to stay updated. Let's build a community of curious minds and quantum enthusiasts together. Ready to explore the building block of quantum computing? Let's dive in. Imagine a world where computers solve problems so complex that today's machines would take billions of years to crack them. That world is closer than you think thanks to quantum computing, and at its core lies the qubit. Unlike the bits in your laptop, which represent either a 0 or a 1, qubits operate in ways that defy classical logic, unlocking incredible computational power. In this video, I'll break down what a qubit is, how it works, and why it's a game changer for technology now. Whether you're new to quantum mechanics or eager to deepen your understanding, this journey will illuminate the magic of qubits and inspire you to explore further. Let's embark on this quantum adventure and uncover the secrets of the qubit. What is a qubit? A qubit, short for a quantum bit, serves as the fundamental unit of information in a quantum computer, much like a bit does in a classical computer. However, that's where the similarities end. Classical bits exist in one of two states, either 0 or 1. You can think of them as light switches. They're either on or off. Qubits, on the other hand, harness the principles of quantum mechanics to exist in a far more dynamic state, opening up possibilities that classical bits can't touch. The magic of a qubit lies in its ability to exist in a superposition of states. Superposition means a qubit can represent both 0 and 1 simultaneously, rather than choosing one or the other. Picture a spinning coin in the air, and it's neither heads nor tails but a blend of both until it lands. In the same way, a qubit in superposition holds a combination of 0 and 1, described by a mathematical wave function. This wave function uses complex numbers to define the probability of measuring the qubit as 0 or 1. For instance, a qubit might have a 70% chance of being 0 and a 30% chance of being 1 when measured. Until you measure it, it exists in this dual state, allowing quantum computers to process a vast number of possibilities at once. But superposition is just the beginning. Qubits also exhibit a property called entanglement, which Albert Einstein famously dubbed spooky action at a distance. When two qubits entangle, their states become linked, so that the state of one instantly influences the state of the other, no matter how far apart they are. If you measure one qubit and find it to be 0, the other qubit might instantly become 1, even if it's on the other side of the galaxy. This entanglement creates a powerful connection that quantum computers utilize to perform coordinated calculations, exponentially increasing their computational power as more qubits become entangled. Another key feature of qubits is quantum interference. Because qubits exist as wave-like states, they can interfere with each other, much like ripples on a pond. Constructive interference amplifies specific outcomes, while destructive interference cancels others out. Quantum algorithms, like those used to factor large numbers or simulate molecules, exploit this interference to zero in on the correct solution faster than classical computers. These properties, superposition, entanglement, and interference, make qubits the powerhouse behind quantum computing's potential to revolutionize fields like cryptography, drug discovery, and artificial intelligence. How are qubits physically realized? Now that we understand the properties of qubits, let's explore how scientists create them in the real world. Qubits aren't abstract concepts. They're physical systems that engineers manipulate to exhibit quantum behavior. Researchers employ a range of technologies to construct qubits, each with its unique strengths and challenges. One common approach involves superconducting circuits, as discussed in the article, Superconducting Qubits, Powering the Quantum Revolution by Quantum Insider. Scientists cool tiny circuits made of superconducting materials, such as aluminum or niobium, to temperatures near absolute zero, approximately 273 degrees. At these frigid temperatures, the circuits lose electrical resistance and behave as artificial atoms, allowing them to enter superposition states. Companies like IBM and Google use superconducting qubits in their quantum computers because they're relatively easy to control and scale. However, they require extreme cooling, which makes them bulky and energy-intensive. Another method uses trapped ions, where scientists trap individual atoms, such as ytterbium or calcium, in electromagnetic fields and manipulate them using lasers. The article Ion Traps: A Path to Scalable Quantum Computing by Nature highlights that ion qubits offer high precision and long coherence times, the duration they maintain their quantum state. Companies like IonQ lead in this technology, leveraging the natural quantum properties of atoms. The challenge? Trapping and controlling ions demand exact equipment, making scaling difficult. Photonic qubits provide yet another approach, using photons of light to encode information. Photons naturally maintain coherence over long distances and interact weakly with their environment, as noted in Photonic Quantum Computing: The Future of Light by Photonics Spectra. Companies like Xanadu utilize photonic qubits for quantum computing, leveraging their potential in quantum communication networks. However, creating entanglement between photons remains a technical hurdle, requiring complex optical systems to generate and detect them. Other methods include topological qubits, which utilize exotic states of matter to encode information in a more resilient manner against noise, and quantum dots, which trap electrons in semiconductor materials such as silicon. Each approach offers unique advantages, but they all face the same enemy: decoherence. Environmental factors like heat or electromagnetic noise can disrupt a qubit state, causing it to lose superposition or entanglement. Researchers work tirelessly to extend coherence times and reduce errors, a critical step toward practical quantum computing. Why are qubits a game changer? Qubits hold the potential to transform industries because they enable quantum computers to tackle problems that classical computers struggle with. Let's explore a few examples to see this power in action. In cryptography, qubits pose a threat to current encryption systems, such as RSA, which relies on the difficulty of factoring large numbers. A quantum computer with enough qubits can use Shor's algorithm to factor these numbers exponentially faster, breaking encryption that protects online banking, government secrets, and more. This capability, discussed in Quantum Computing's Threat to Cybersecurity by Forbes, underscores the need for quantum-resistant cryptography to safeguard our digital world. In drug discovery, qubits simulate molecular interactions at the quantum level, a task classical computers find daunting. For instance, a quantum computer can model how a drug binds to a protein, speeding up the development of new medicines. The article Quantum Computing in Pharma: A New Frontier by Pharmaceutical Technology notes that companies like Merck explore quantum simulations to revolutionize drug design, potentially saving years and billions of dollars. Qubits also optimize complex systems, like supply chains or financial portfolios. Quantum algorithms can evaluate countless scenarios simultaneously, finding the best solution faster than classical methods. This ability to handle vast datasets with speed and precision positions quantum computing as a transformative force across industries. Qubits are more than just a scientific marvel. They're the key to unlocking a new era of technology. Their ability to exist in superposition, entangle with each other, and harness quantum interference opens doors to solving problems we once thought impossible. But the journey has just begun. Dive deeper by exploring how companies like IBM, IonQ, or Xanadu build qubits in their labs. Research the latest advancements in quantum error correction to see how scientists combat decoherence. Think about how qubits could impact your life. Could they secure your data or accelerate breakthroughs in your field? The quantum revolution is here, and you're at the forefront. Keep asking questions, stay curious, and let's explore this quantum frontier together. What an incredible journey through the world of qubits. We've uncovered their properties, explored how they're built, and glimpsed their transformative potential. Now, I want to hear from you. Drop your thoughts, questions, or video ideas in the comments. What excites you most about quantum computing? If this video sparked your curiosity, hit that like button, subscribe, and ring the bell for more fascinating content. Let's keep this conversation alive and inspire each other to dive deeper. Until next time, keep exploring, and I'll see you in the comments.